going to prove the log rules using integrals. The first one, let's call it a rule or a theorem, that, well, like I said, we're going to be using natural logs. The natural log of AB is equal to the natural log of A plus the natural log of B. Like I said, we're going to prove this using integrals. Now, the first thing, let's just talk about this first. So, ln of A is equal to the integral of dx over x from 1 to a. Or is it? Let's just prove it. The integral of dx over x is ln of x from 1 to a. I'm going to assume that all the arguments are positive. So we get ln of a minus ln of 1, and ln of the number 1 is 0. ln of a minus 0 is ln of a. So yes, this is the definition of ln of a. So, now basically, they're ln of anything. I don't care what argument I put in. This is going to be the integral of dx over x from 1 to the anything. Because if you think about it, if a was anything, I would just put anything here, and I would get ln of anything minus ln of 1, which is ln of the anything. Okay, so let's come back here. So therefore, ln of AB, this would equal the integral from 1 to AB of dx over x. Now, in mathematics, you should always try to at least get some pieces of what you want. We want ln of AB to equal to ln of A plus something. So you know what? Instead of going from 1 to AB, I'll go from 1 to A. That is, this part right here is ln of A. I have part of the answer. Plus the integral of dx over x, and I'll pick up at A, and then I'll go all the way up to AB. Now somehow I need to show that's ln of B. So far the first integral is ln of A, and I need to show that this integral is ln of B. So ln of A plus another integral. Now with this integral, I would love to have 1 to B as the limits of integration. What I'm going to do is I'm going to let x equal to, say, a times u. That way, if x is 1, x goes from a to ab. If x is a, then u is 1, because a times 1 is u, is a. A times 1 is a, so the lower limit is 1. And if x is ab, then that equals a times u. Well then, u must be b. So I have the right limits now. I'm going from 1 to b. Now let's look at what dx is, because I need to have x on the bottom, and I know in terms of u, I know what that is. So I have x, I need to have dx. So I take the differential with respect to x on the left and with respect to u on the right. And I get dx can be replaced with a du. And look at that, 1 to b. Look at that. I now have equal to this ln of a plus this integral is integral from 1 to b of du over u. That's just ln of b. And the first theorem has been proved. Now, let's prove this next rule. That ln of a over b is ln of a minus ln of b. So we'll start off with this side. Ln of a over b, ln of anything, is the integral of dx over x from 1 to the anything. And like before, let's try to get ln of a. Instead of going from 1 all the way up to ab, let's stop off and say hello to a. And then let's pick up at a again and go to where we really wanted to go to, namely a over b. And we have dx over x. Now the reason we want that is because the first integral we know, that's ln of a, plus the integral from a to a over b of dx over x. Well, this is ln of a plus, I would love, now this is x equal and this is x equal. I would love a to become 1 in our substitution. And I would just love for the upper limit to become b. Well, if I let x equal to a over u, well, if x is a equals a over u, that happened when u is 1. A over 1 is a, so u is 1. And now, if x is a over b, then let u become b. If u was b, this would be a over b equals a over b. So u is b. Now, if x is a over u, also written as a u to the negative 1, well then dx would be negative a, I brought down the power, u to the negative 2, du, which is the same as negative a over u squared du. So we have dx, which is what we just said, negative a over u squared du, over x, which is a to the u. Now let me erase this mess over here, and let's clean this up a little bit. Now, I'm not sure where I put equal. The first thing I'll say is, let's bring out this minus, so now it's minus. So what is a over u squared divided by a over u? Well, instead of dividing by a over u, we can multiply by the reciprocal. And the a's cancel out. You get u over u squared, which is 1 over u. Okay, so we have ln of a plus the integral from 1 to b of this mess with the minus in front, which is 1 over u times du. So that antiderivative is ln of u. Well, if you go from 1 to b, oops, we have one typo. If you go from 1 to b, you get ln of b. But as I said before, when I bring out the minus, it becomes minus. And by error, I wrote plus. So we're getting the right answer. Ln of a divided by minus ln of b. Ln of a minus ln of b. That is what it says at the very beginning. Ln of a over b is ln of a minus ln of b. Now, there's one more rule that I would like to prove using logs. Ln of a to the r times ln of a. The proof is going to be done the same way. Ln of anything, and that's the anything, so I put the brackets around. This is the integral from 1 to the anything of dx over x. Now, I really want it to go from 1, the limits to go from 1 to a. So that will give me the ln a. Hopefully the r will magically appear. Well, if I let x equal u to the r, if I let x equal to u to the r, well, when x is 1, u must be 1. Because 1 to the r, or 1 to any power, is 1. So 1 to the r is 1, so u is 1. Now, if x is a to the r, a to the r is u to the r, well then, since the powers are the same, the bases must be equal. U must be a. Ooh, looking good. So then dx is r u to the r minus 1 du. So the question is, what is dx over x? I'll work that out right here. Dx over x. Well, dx is, in the u world, is ru to the r minus 1 du over x, which is u to the r. Okay, the only thing we can really simplify is that. The r stays on the top, the du stays on the top, and u to the r minus 1 divided by u to the r leaves the u in the bottom. Okay, so dx over x is this. Ooh, look at that. It's r du over u. The r being a constant, I can factor out in front, and the proof is now done, because I have r times this, but that's ln of a. So yep, you definitely can bring that power down. I know you can. We just proved it. You know what? For bonus, let's prove all of these rules using the definition of logs. So for example, if you have the log base a of xy, we want to show that this is log base a of x plus log base a of y. Okay, this is a fact or a theorem, and I'll prove it. How about I let u equal this, log base a of x, and I let this be v, and v is log base a of y. So writing this exponentially tells me that a to the u is equal to x, and writing this exponentially tells me that a to the v is y. Now, I want to know about xy. Okay, so x times y is x, which is a to the u, times y, which is a to the v. This is a to the u plus v. So let's write this down again. xy is a to the u plus v. But you know what? This is the same as log base a of xy equals u plus v, because a to the other side of the equal sign is equal to xy. And that's exactly what it says here. Okay, now one last thing. U is log a x, log base a x, plus v, which is right here, it's log base a of y. So I just shown that log base a of xy equals log base a of x plus log base a of y. And I proved this. This is now valid. Suppose we have log base a of x over y. I want to show that this is log x minus log y. As long as all the bases are the same, don't even have to really say the base. So I'm going to start with this, and I'm going to show that it equals to that. Okay, and the proof is the same way. Let u equal to log base a of x and let v equal log base a of y. So this tells me that a to the u is x, and this tells me a to the v is y, and I want to talk about x over y. So x over y is x a to the u over y. Now here is why we get subtraction, because now we subtract the powers. So we really ignore this. This is equal to that. That's an exponential equation. We can write it in terms of logs. It's log base a of x over y is equal to u minus v. This equation in blue, let me say it slightly different. That exponential equation in blue and this logarithmic equation in blue, they're the same. Now u is log base a of x minus, it does say minus, v is log base a of y. So I just shown that log base a of xy is log base a of x minus log base a of y. That is the fact that I wanted to show from the start. Let's do one more. Want to show that, so theorem or fact, log base a of x to the r is r log ax. I guess you can do this by induction, but we won't do that. So you have r log base x. Well, let's call that u. So this tells me that a to the u is x. Well, we want to have x to the r. Okay, so I'll raise both sides to the r power. So now I have x to the r is a to the r times u. And if I write this, this is an exponential equation. If I write it down as follows, log base a of x to the r is equal to r times u, which is r times u. But u is log base a of x. Log base a of x. So yes, you can bring the power down. But this actually needs to be spoken about for a moment. For example, if you have log base 3 of negative 2 squared, which is log base 3 of 4. Okay, I meant to say negative 9. Log base 3 of negative 9 squared is 81. And this is well defined because 3 to the 4th power is equal to 81. 3 times itself 4 times is 81. It's 9 times 9 is 81. Do not say 3 times 3 is 9 times another 3 is 27, because then you're going to say you don't know what 27 times 3 is, need pencil and paper or a calculator. Why not say 9 times 9 is 81? Okay. Now, so 4 is equal to log base 3 of negative 9 squared. And according to this rule up here, you can bring the power down in front. This becomes 2 times log base 3 of negative 9. And the real response is, no it doesn't, no it doesn't. Because although I understand quite well what 2 times something else is. I don't know what that something else is. This is saying, let's look at it down here, please. This is saying 3 to some power is negative 9. This is the same statement as 3 to some power is negative 9. But 3 to no power is negative. That is, this here is not defined. This equation or this expression is not well defined. Okay, that is, this is well defined, it's 4, but this here, or that, you can say the whole right side, but in particular, what's in the blue box now is not well defined. So I don't know what 2 times I don't know equals. It certainly doesn't equal to 4. Okay, it certainly doesn't equal to 4. So you can only bring the R down if the base is positive. If the base is negative, you can't bring the base down. Okay. Now, let us prove one other theorem. The change your base theorem. If you have log base A of B, you can pick any other log you want. Sorry, any other base you want. Say base C. But this time, you're going to have to divide log base C of something by log base C of something else. Visually speaking, this is higher than the A. The higher one goes higher, that is the numerator, and the lower one, which is A, goes down. So what this is saying is, if you have log base 7 of 8, you can't even calculate this on a calculator, but you can use log base E, which really means ln. This number on top, this number on the bottom. That is, you can use ln of 8 over ln of 7, and you can use your calculator and get an exact answer. Or you can use log, which means log base 10. You can use log base 10 of that number divided by, keep the base the same, log base 10 or 7, which shorthand is log 8 over log 7. If you have a strange calculator and it has log base 3, log base 7 of 8 is equal to, well, the 8 is higher looking, so it goes in the top. The base is a lower number, it goes in the bottom. You can use that special calculator to compute log base 3 of 8 divided by log base 3 of 7, and you'll get the same answer. Whatever this is, whatever this is, whatever this is, whatever this is, same answer. Same answer. It's called the change your base theorem. Okay. So, let's prove this. Log base A of B is equal to log base C of B divided by log base C of A is the same statement as this times this equals that. Those are the same statements. So, log base C of A times log base A of B is equal to log base C of A. And of course, that should have said log base C of B. Sorry. In other words, if I show that this is true, I'll divide both sides by log base C of A, and I will get this. They're the same, these two are the same statement. Okay. So, let's work on this. Let u equal log base c of a and v equal log base a of b. So if this is u and this is v, I would love to show that u times v equals that. They need to get things in terms of exponential, I think. This tells us that c to the u is a. And this tells me that a to the v is b. Now, this is asking, this here is asking c to what power gives me b. Okay? C to what power gives me that. Now, I have c to a power equals a, so I don't have c to a power equal b, but I know a to a power that equals b, so what I'm going to do is I'm going to raise both sides to the v power. For one reason, a to the v is b. So we have c to the u raised to the v, which is c to the uv. This is a to the v, which is b. Because a to the v is b. Ignore this. That is c to the uv is equal to b. But this statement is exponential. I'm going to write it in logarithmic form. This is log base c of b is equal to u times v. I got it. Log base c of b is exactly what it says here. I want to show that it equals to u times v, because u is log base c of a times v, which is log base a of b. Okay, so I did establish that this is equal to this. So if this statement is true, which is what I have on the bottom, then this statement is true. That is, this theorem is true. Now, just want to look at this a little bit more closely, especially as a product. So we just learned that log base c of b times log base, well, let me write it down correctly, I'm sorry. Log base c of a times log base a of b, log base a of b is equal to log base c of b. Now, if you think of division for a moment, these kind of, in some ways, cancel out. And you're left with base c of b. Exactly what that is. In other words, if somebody asks you, what's log base 2 of 3 times log base 3 of 4 times log base 4 of 5 times log base 5 or 6 times log base 7 of 8, 6, 7, log base 6 of 7, log base 6 of 7 times log base 7 of 8, you should quickly say it's 3. And the reason is as follows. You can cancel that, and this and that, and this and that, and 7. So what you're left with is log base 2 of 8. And since 2 to the third power gives me 8, this mess is 3. That's 3. Okay, you don't have to know what this base is. Sorry, what that log is. You don't have to know what that log is. Don't have to know what any of these logs are. Just know that it simplifies out to log, well, the 3's cancel, the 4's, the 5's, the 6, the 7's. All that didn't cancel was the base 2 and the 8. So it's 3, or log base 2 of 8. Now, if you were asked to calculate log base 2 of 8, and you didn't see it was 3, and you did all this work, and you're like, I'm not going to get full credit or any credit unless I give the exact answer. Well, and you have a calculator. You can use the change of base theorem. Log base 10, log base 10. This number goes on top. This number goes on the bottom. And if you use your calculator, you'll get 3. If your classmate instead says, you know what, my log button's broken, or I don't like logs, I like natural logs. Noah, calculate that on your calculator, you'll get 3. Calculate log of 8 over log of 2, you'll get 8. If you had a calculator that did log base 17s, well, log base 17 of 8 divided by log base 17 of 2 is also 3. It doesn't matter what base you use. That's what this theorem is telling you. And we proved it. Okay, that's going to complete this video on proof of the log formulas. We proved the log formulas using the definitions, and we proved the ln formulas by using integration. If you like this type of mathematics, please subscribe to my channel. Leave comments below. Let your friends know about it. Thank you.